The second test we will look at is a highly dynamic situation of a motor at 5,000 RPM and zero torque initially with a 70 Newton meter load step. The electrical characteristics respond very quickly, and what I have displayed on the screen is just the torque. In the red we have full bandwidth torque, in the blue we have a 10 Hz filter torque, and finally in the black is the cycle average torque that is calculated the same way as the previous section. The 10 Hz filter is something I see very frequently in the field with competitors, so I wanted to show it here. The dynamic reading in red really attracts your attention because there's a dramatic peak up to 105 Newton meters and a valley down as low as 35 Newton meters. This is what is actually happening with the torque. The motor controller is reacting to the load step and has some mechanical dampening and control settling time. In total, it takes about 1/10 of a second for the system to settle to the commanded 70 Newton meter value. At the end, once it has settled to that 70 Newton meter value, we still see that there's a cyclical ripple that we refer to as torque ripple. This type of knowledge can be very valuable when determining what is actually happening with the motor system, sizing of components, and tuning of the controls. To relate this phenomena to electric cars, it would be the feeling that a driver gets when stepping on the gas pedal and feeling the car stutter when it takes off. By knowing what the torque is actually doing, we can make efforts to control it better. With the dynamic torque, we also know the exact timing of when torque is applied. Systems that have filter have a phase delay. The first thing that should catch your attention is the delay between the red full bandwidth signal and the blue filtered signal when the load step is applied. The rise time is severely delayed with the low filter setting, and all the dynamics are lost with the blue filtered signal. Eventually, the value of the filtered signal is the same as the cycle-based average, but we do not see the torque ripple dynamics, and it's also much slower than the cycle average, really giving you the worst of both worlds. The cycle average torque in black, it's almost instantaneously at the commanded value. This is because we are taking a nice time average of all the points that are going equally higher and lower than the average even during the settling time. This gives us a reliable number for efficiency readings, but no sense of dynamics. The cycle-based nature of the calculated average makes this a very accurate solution even when doing dynamic testing, but you do not get the peaks and valleys that you see with the full bandwidth torque. The combination of average value and instantaneous value make the high bandwidth torque cell in combination with the eDrive system a very powerful tool for understanding both the dynamics and averages of an electrical mechanical system during load steps.